Hi everyone, I'd like to begin this module on work and energy by talking about the question, what is energy? If you look this up, you might find the definition that energy is the capacity of a system to do work. And then if you go look up the definition for work, you might see that work is a transfer of energy. So these definitions are often cyclic, which makes energy really hard to define on its own. You can think of energy as a measure of the capacity of a system to make things happen, or in the case of stored energy, the potential to make things happen. The unit of energy is joules, the SI derived unit, and 1 joule is 1 kilogram meter squared per second squared, or we could write 1 Newton meter. Let's talk about some common forms of energy. In this module, we'll focus on kinetic energy, which is the energy that an object has due to its motion, and potential energy. Potential energy refers to stored energy, and there's many different types, but we'll focus on gravitational potential energy and elastic potential energy, and I'll introduce those two quantities later. A system's total mechanical energy, E, is the sum of its kinetic energies and potential energies. And when we use system in this module, it means an object or a collection of objects. And later on, we'll look at conservation of energy, and we'll see that energy can exchange between forms within a system, but work must be done on the system in order for there to be a transfer of energy to the system. Okay, let's begin 6.1, work. Work has a very specific definition in physics. It's the transfer of energy to a system caused by a force acting on the system over a displacement. So this is a transfer of energy, so work is also measured in joules or in Newton meters. And let's look at the definition now. Let's start by looking at the work done by a constant force, F, as it acts on an object over displacement d. Before we use delta r to mean displacement, your textbook uses d to mean the magnitude of a displacement in the work formula, so I'll use that as well. So the formula to calculate the work done by this force F is work, W, equals Fd cos theta, where work is measured in joules or Newton meters, as I said. F is the magnitude of the force, so it's positive, in newtons. D is the magnitude of the displacement, also positive, in meters. And this is cosine of theta, where theta is the angle between the force and the displacement. So this will give you the work done by the force F. So this is for an individual force. Also, work is a scalar quantity. It's not a vector. We have two scalars here and cosine of theta. This is actually a dot product of vectors. That's where this relationship comes from, and it produces a scalar. However, work does have a sign associated with it. If the work done on the system is positive, so W is greater than 0, that means that the force caused an increase in energy to the system. So that's an energy gain. And of course, the overall change in energy to the system depends on the net work done. If the work done is less than 0, that means that there was an energy loss to the system caused by that force acting over a displacement. Let's look again at the formula for work. Work equals Fd cos theta. So there are also 3 cases where there's no work done on the object by the force acting on it. And the cases are here. The first one is when F equals 0. So this might seem obvious. There's no force acting on the object, then of course it doesn't do any work. But it also applies to the net force. If the net force acting on an object is 0, then there's no net work done on the object as well. The next one is when d equals 0. If the object doesn't move, there's no displacement, then there's no work done on that object as well. We need to have a displacement in order for work to be done. So that means that no matter how hard you push on an object, if you're pushing really hard, you feel like you're doing a lot of work, but it doesn't move, technically no work is done. The last case is when cos of theta equals 0. Cos of 90 degrees equals 0. So when theta is 90 degrees, no work is done. Theta is the angle between the force and the displacement, so this means that forces that act perpendicular to a displacement do no work on the object. So that's something important to remember, and we'll see some cases where no work is done by a force in the examples. Often we'll need to calculate the net work done on an object, especially as we get into the work kinetic energy theorem. So there's two ways to calculate the net work done on the object. The first way is by summing the work done by all of the individual forces acting on the object. So we have the net work equals the sum of all of the individual works done on that object. And this method is useful especially if you've already found the work done by each force. The other way is to use the net force. Or we have the net work done on the object equals the net force times the magnitude of the displacement cos theta. So alternatively, we can find the net force and then find the work done by the net force. Just make sure that if you're using this second method, that theta is the angle between the net force and the displacement in that case. Okay, let's try some examples. Example 1, a 10 kilogram box sits on a frictionless floor. A 50 Newton force is applied to the box at a 45-degree angle above the horizontal. Calculate the work done by each of the forces on the box if the box moves 1 meter to the right. Okay, so I've drawn the free body diagram here. I think it helps to also draw in the displacement if we're looking at work problems so that you can clearly see the angle between each force and the displacement. First, let's look at the work done by the normal force. The normal force is perpendicular to the displacement. It's at an angle of 90 degrees. So the work done is 0. This is because cos of 90 is 0, which we've talked about before, so the work done by any perpendicular forces is 0. The same goes for gravity. The angle between the displacement and gravity is also 90 degrees, so it's still a perpendicular force and the work done is 0. So the only force that does work on the box is the applied force. We have the work done by Fa equals FAD cos theta. So 50 newtons times 1 meter cos 45. And this is 35.3 Newton meters. Example 2, a 10 kilogram box sits on a floor. A 50 Newton force is applied to the box at a 45-degree angle above the horizontal. Its motion is resisted by a 12 Newton friction force. A, calculate the work done by each of the forces on the box if the box moves 1 meter to the right. And B, calculate the net work done on the box. So we've already looked at this situation in example 1. The difference now is that there is friction acting on the box. So I'm just going to add in the force of kinetic friction, which opposes the motion of the box. So it's going to be in the opposite direction of the applied force here. Again, we know that work done by the normal force and gravity are 0 since they're perpendicular to the displacement. And we found the work done by the applied force, and it's the same applied force for this example. So we need, for part A, we need the work done by the kinetic friction, which will be FKD cos theta. So the friction force is 12 newtons. We have 12 newtons times 1 meter. And then cos of 180 degrees. So the angle between the displacement and the friction is 180 degrees since they're in exactly the opposite direction. And you can check cos of 180 is -1, so this gives -12 Newton meters. All right, now for part B, when we look at finding the net work, since we've already found the work done by each force individually, we can add them up to find the net work done on the box. So 0 plus 0, then we have 35.3 Newton meters minus 12 Newton meters, which is 23.3 Newton meters for the total work done on the box. So we have the applied force adding energy to the system and friction removing energy to the system to leave an overall net positive work done.